And let's get started. Hi, everybody. This is a small crowd, and that's good. That means you can stop me at any point and ask questions, and we won't get too far off target. Welcome to DevNation. Welcome to Boston, if this isn't home. My name is Christine Flood, and I'm here to talk to you about Shenandoah. It's a new garbage collection algorithm that we've been developing here at Red Hat. This is joint work with Roman Kenke, Rael Viroy, and myself. So I want to start out by saying this is a work in progress. I'm just telling you about some cool stuff we're doing at Red Hat. We're not in a position for you to be running this in your production servers yet, hopefully by the end of the year. So Java had three big ideas that it brought to most programmers, production programmers. Write once, run anywhere, portable multi-threading, and garbage collection, or implicit memory management. And I'm here to talk to you about garbage collection. I honestly didn't know. I've never spoken at DevNation before, so I tried to do my slides from beginning to end, from soup to nuts. So if you're garbage collection experts, I apologize. The benefits of garbage collection. Imagine that you had an omniscient housekeeper that would come in and organize all the papers on your desk. She could get rid of all the ones you weren't ever going to use, and all the ones you needed were all neatly stacked and compressed in one area, giving you lots of room to work. That's what the garbage collector is doing for your memory. Anybody that's ever had to debug a stray pointer knows how valuable garbage collection is. It frees you from having to track those things down. And they're really miserable, right? Because you don't have any history of how you got to this bad place in memory. You just know that you're there. And that leads into safety. Because you aren't programming with pointers, you have less likely to go off into somebody else's memory or to do bad things. You have fewer memory leaks. Now, I had the need to be intellectually honest there. It's still possible to get a memory leak in Java. If you had a linked list of every object that you've ever created and you keep adding to it, your memory is going to keep expanding, but there are fewer of them. Better cache locality. Because we're compacting all of our objects in the heap closer together, you're more likely to get cache hits. Less memory fragmentation. Because we're moving all of your objects to one side, we're giving you this big contiguous region that you can allocate out of. And that gives you the ability to do fast allocation, right? Pointer bump allocation makes your whole Java program run faster. So the downside to garbage collection is pauses. I love this graphic. You've got your Java threads are all running. They're trying to get stuff done, and then they hit a GC pause and they stop. And then they're running, getting stuff done, and they hit a GC pause and they stop. So this sort of starting and stopping behavior can be frustrating. And its expenses have changed over the years. I worked on Lisp machines back in the day, in the 1980s, and when you hit a garbage collection pause, that meant you went out and you got a cup of coffee. I also worked on garbage collection again in the early 2000s, and what that meant was that your telco app would drop a call. And now, in 2015, a garbage collection pause is actually costing you money. And why does it cost you money? If you've got a stock trading application and your garbage collection causes your Java program to go offline for 30 milliseconds or even a minute, then you're not making the trade at the optimal time and it's costing money. If you have an e-commerce website and you get a garbage collection pause, your user might get distracted and go off and read Dilbert or something and not press the buy button. And there are some people that have to make applications with quality of service guarantees, and they can't do it because the garbage collection pause keeps them from being able to guarantee 10 millisecond response times or 15 millisecond response times. Now, Shenandoah is not completely pauseless. We still have pauses, but our pauses are much shorter. And hopefully some of these people that just need soft real-time response time can run on Shenandoah, whereas they couldn't run on the current collectors. So again, application requirements have changed over the years. In 2000, we had telco applications that were using 200 megabytes a heap, and they needed 50 millisecond pause times. Here in 2015, we've got applications that are using 100 or 200 gigabyte heaps, and they're saying we want 10 millisecond pause times. So to do that, we need the next leap in garbage collection technology, and that's what Red Hat is working on. So what can we do to shrink your pause times? What we do is we increase concurrency. The more work we can do while your Java threads are running, the shorter the pause times need to be. So what Shenandoah does is we compact the objects while the program is running. So our goal is to have sub 10 millisecond GC pauses for 100 gigabyte plus heaps. How does it work? We divide your heap into regions, each of which can be collected independently. We are concurrent, which means we do work while the Java threads are running. We're also parallel, meaning we can use as many threads as you have spare to give us to be able to keep up with the mutator. And we're a compacting collector, meaning that we do move all of the objects up in space to give you that big contiguous free area to enable pointer bump allocation. So, like I said, we divide our heap into regions that are independently collected. We're concurrent. We use a concurrent GC thread to mark the live objects. So here you can see with our 5 heap regions, we have 3 of them that have less than 50% live, and we have an empty one. That's all determined while your program is running. And we do the compaction while the program is running. So we can take those 3 partially full regions and compact them while the Java threads are running. We can use as many threads as you have available. Generally, this means that you need to dedicate some threads, some hardware threads, to concurrent GC. So how do I compare and contrast this to what's out there now? Currently, there are 4 possibilities for what you can run when you run OpenJDK. You can run the serial garbage collector, which has small footprint, small overhead, and uses a minimal amount of resources. So let's say you were running 20 VMs on your server. You might want to run the serial GC because that's the most predictable and the smallest use of resources. We have the parallel garbage collector, which is the high throughput collector. If your goal in life was to run fast Fourier transform as fast as possible, parallel GC is going to give you the best time to your answer. Parnu CMS was built to minimize pause times. This is not a compacting collector. You still have pointer bump allocation some of the time, but when you promote things to your old generation, which I'll explain in a little bit, that's done with free lists and finding the best block to fit things in. The problem with that is that eventually, as with any free list-based allocation system, you're going to eventually get too fragmented. You'll have plenty of space free, but you won't have enough contiguous space free to allocate what you want. And then G1, whose goal was to manage pause times. And the way that works is it's built a region-based one like Shenandoah. You pick the regions that you want to compact based on how long it's going to take to copy the live objects. So you can set a goal with G1 saying, I want my pause times to only be 15 milliseconds. And it will work very hard to keep the regions that it picks to fit within that 15 millisecond pause time. But eventually, if your pause times are too small, if your goals are too small, it's not going to keep up with the mutator activity, and it's going to end up falling back to a full GC. Do we have any questions on these slides? Do these slides make sense? Yes?
How does the different flavors of the garbage collection compare to the VM shipped by Oracle and the one from IBM?
IBM has a pauseless, a so-called pauseless collector. I hate that term because it's not really pauseless. It's just very short pauses. IBM has one. Oracle doesn't have one. Our goal is to put this back into OpenJDK, which will then end up in Oracle's VM, presumably. Fingers crossed. My goal is to get it put back upstream. So here's just a pictorial of what the serial GC looks like. The green threads are your Java threads. You've got a bunch of them are running along, they stop. They do a small collection, a young generation collection, and that's the red pause where no Java work happens. You do some more Java work, and then you have an old generation collection which stops for even longer. Parallel GC was the next step up, where you would use multiple GC threads to get the work done. CMS and G1 all had a concurrent thread that worked while the Java threads were running, but all they did was the marking of the heap. They didn't actually do any evacuation. So they both end up with with full collections that take a long time at the end. So here's what Shenandoah looks like. We have our Java threads running. We have to stop the threads for long enough to scan the Java thread stack, all the globals, and get the current state before we set up an initial mark. CMS and G1 both do this as well. They piggyback on a young gen collection. We run the Java threads again, and we do a final mark. Again, this is a short mark. All we're doing is scanning the Java threads. So this should be under 10 milliseconds, assuming you don't have thousands and thousands of threads with very deep stacks. And then we start up and we do the concurrent evacuation. I drew on here that we have 2 threads for concurrent mark and concurrent evacuation, but really you can use as many threads as you can assign at the command line as many threads as you want, and we will use them. So why aren't we truly pauseless? I tried to anticipate your questions. This isn't the first time I've given this talk. One thing we could do is we could stop the threads in a round-robin fashion and only stop one thread at a time to scan the stack. But that's a theoretical result, and there are collectors that do that. But right now, we don't know if it's going to be practical or not. Just being able to lower the pause times to just the scanning of the thread stacks is a huge step forward, and that's what we're focusing on right now. So how do we compact objects while the Java threads are running? Like all problems in computer science, I love this line, we added a level of indirection. What we've done is when we allocate objects, we allocate a single pointer preceding the object that tells you the address of the current address of the object. So all accesses go through that forwarding pointer. This is a very fast read barrier. What we do is we have an address to an object that we want to access. We read the address -1, and then we read the contents of that. It tends, in most cases, to be an in-cache read. And from all our measurements, this is not a performance problem for us. It's the thing most people are worried about, but it's just not an issue. All right, but it does have a space cost. In the worst case scenario, if all of your objects are the smallest that they could possibly be, it's going to be a 25% overhead. But we use less implicit space. I don't know if any of you guys have ever tried to run Java and said, I want a 256 megabyte heap, and then gone and done a PS or a top and looked and seen that, oh my gosh, I'm running with 300 megabytes or 320 megabytes. The VM has internal data structures that are what I call implicit space. And we actually have fewer of those. So we use less implicit space. So how do we actually copy these objects while the threads are running? What we do is we make a speculative copy. So the garbage collector has thread local storage that it allows it to make a speculative copy of foo. And then it will try and do an atomic compare and swap. Does everybody know what a CAS is? So if the location has what we expected in it, meaning it still points to the from space object, we want you to update it to point to the to space object. If that CAS succeeds, then we're golden. Everybody now agrees on where the one true copy of foo is. Both the compiler and the garbage collector all know where it is. If that CAS fails, that means that somebody else CASed in a forwarding pointer before we got to it. And we all agree that foo double prime is the one true foo. And moving forward, that's the copy of the object we use. Because we made this speculative copy in thread local storage, we can roll it back. So that space is not lost. All right, so the one complication here is that we need a more complicated write barrier. We need to ensure that writes only happen on the 2 space copies. So the Java threads have a write barrier that makes them responsible for moving an object if it's in from space. It first moves the object and then it writes to it. And that's because if we allowed writes to happen in the from space copy, there would be a race. There would be a speculative copy and somebody could be writing the 17 while we're installing the forwarding pointer, and that write would get lost. So let's go over the costs and the benefits. The cost is you have an extra word per object, and that can be expensive if you have a lot of small objects. The cost in time is that we have the read barrier. It's very fast, but it's still there. And we have a slightly more complicated write barrier when an evacuation is in progress. The benefits are that our pause times are very low, and that's important to interactive and quality of service applications. So how is Shenandoah different? We compact the objects while the Java threads are running. CMS doesn't perform compaction unless you do a full GC. G1 stops the world to move objects. We move them while the Java threads are running. And our pause times are proportional to the number of threads and the depth of their stacks, as opposed to being proportional to the amount of live data that has to be copied during the GC pause. All right, so our current status, we have something working. We can pass most tests like SpecJVM and SpecJBB, and we're working on performance tuning, in particular Radar Gun, which is the JBoss data grid, and Elasticsearch/Lucene, where we have a test case for those as well. We think that once we have everything working, we should be able to do really well on, say, SpecJBB 2015. Unless, of course, you compare us to people that just allocate, terabytes of heap and don't ever garbage collect, in which case they'll do better. So one of the questions that I've gotten quite a bit is, why isn't Shenandoah generational? Everybody learned in, Lisp 101 or Java 101 that generational collectors were faster. The generational hypothesis says that in most cases, young objects are more likely to die than old objects. This is certainly true for languages like Smalltalk and Lisp, where you're doing lots of small allocations. It was true for SpecJVM 98. It's not quite clear that it's true for our applications in 2015. So we want to push non-generational Shenandoah as far as we can before we revert to a generational GC. So what do I mean by a generational GC? Most, except for G1, most of the garbage collectors in OpenJDK look like this. You have an Eden where you allocate, when things survive, they get promoted to your semi-spaces, where they get copied back and forth some number of times, and then they get promoted to the old generation. So the way you collect just the young generation is you have a card table, and that card table keeps track of all the pointers in the old generation that point back to the young generation. And this allows you to collect the young generation by itself. So this is one of those implicit data structures I was talking about that's required for the other collectors. And if your application really behaves in a generational fashion, this is a huge win, because by the time things get promoted to the old generation, you assume that they're going to be around for a long time. However, here's an example that I came up with of an application that generational GC might not work well for. Imagine that you were caching you had a web URL cache where you get URLs and you map them to a whole bunch of objects that represent web page content. So if this is a least recently used cache, when a new URL comes in, it's going to evict URL 1. And URL 1 has been around long enough that it's probably been promoted into the old generation. So when we add URL 4, we end up evicting URL 1. So what this looks like in a generational collector is you've added URL 4 to the old generation because that's where your hash table is. But all of the web page content is allocated in the young generation. That's going to get copied from Eden to FromSpace, from FromSpace to ToSpace, and eventually promoted. Meanwhile, the stuff that's actually garbage, the stuff that was pointed to by URL 1, isn't going to be collected until you get to an old generation collection. This is one of those cases where a generational collector may not buy you anything, but something like Shenandoah, or G1 for that matter, G1 can do this too, will focus the garbage collection energy on the regions that have garbage. So we'll actually be targeting whatever region has that garbage web page content, and that'll go away. So as I said, Shenandoah, if your application is generational, Shenandoah will behave in a generational fashion. If your application behaves more like a cache, we're going to concentrate our energy where there's actually garbage. So people ask me, how do I run it? It's just a command line flag like all the other garbage collectors. It's just a -XX option. We currently don't run with compressed oops, and you're probably going to want to specify concurrent GC threads, but that's all you really need to do to get it. So when would you want to use Shenandoah? Probably if you have a heap that's greater than 20 gigabytes. If you're running with a 100 megabyte heap, you're probably going to want one of the other collectors. It's only when your heap is big enough that your pause times are onerous that you're going to want to move to Shenandoah. And you're probably going to want to have some extra hardware threads so that the GC threads are not fighting with the Java threads for resources. So what are we doing? We need to finish our big application testing. We need to get more stability. And we have some heuristics tuning to do to get the best performance. Things like when do we start a concurrent mark? How many regions do we have in our evacuation set? Those things. We're still working on tuning those to get the best performance. Wow, I think this is a record for me for shortest talk ever. Feel free to download the code. We want to hear what you think. It's all there. It's all open source. It's the bleeding edge where our development is happening. We have a couple of blogs where you can read about the genesis, how we got to where we are with the design. And feel free to email us, and we're happy to answer any questions. And believe it or not, I am done in record time. So are there any questions I could answer? Does anybody have any burning GC issues? Yes?